online. For those who are here in person, I hope that yesterday the barbecue was nice, was recharging for you. The first 2 days were packed with a lot of concepts, very important ones that we will also use in this lecture. And now, today and tomorrow, yes, we are going to tell you about some more, something more about deep quantum gravity in two different approaches, asymptotic safety and string theory, that will be done by Viano. So I will start with a recap of what we have done in the past 2 days, at least the concepts that will be useful for this lecture, and an introduction to the topic. And then we will continue with some concepts. Okay, wait, I'm probably writing too small once again. Yeah, I have to renormalize my writing. Okay, so start with recap and intro, and then some concepts about non-perturbative renormalization and asymptotic safety. And at least for the first hour and a half, I don't want to be too technical. I just want these concepts to be very, very, very clear, so crystal clear, because once we go into non-perturbative computations, stuff can get very wild, very difficult, very easily. And therefore, it is important to have the motivation in mind and know where we are heading to. And in particular, among the concepts, I'm going to tell you about the Wilsonian idea of renormalization, asymptotic safety, and how to re-understand some perturbative statements in terms of the non-perturbative concepts, in terms of the Wilsonian renormalization. So re-understand, or better understand, standard perturbative renormalization or perturbative statements. And this essentially will cover the first part of today's lecture. And later, we will move on with deriving the so-called vectorish equation, which is a non-perturbative all-order version of renormalization group equations that is very useful to understand the structure of renormalization group flows beyond the perturbation theory. And, well, of course, its properties and its consequences. And hopefully, at some point, probably tomorrow, we will reach the case of gravity and asymptotic safety. That is always the shortcut, this AS for asymptotic safety. And then we will go into some milestones, achievements of this field and open questions. How does this connect with everything that we have seen so far? Well, first of all, Luca did a very good job at introducing concepts that are very useful in general in quantum field theory, like gauge fixing, Faddeev Popov ghosts, and propagators. That is very important to test unitarity in theories of quantum gravity that are based on quantum field theory. But he also mentioned towards the end of his lecture what is, in a sense, the starting point for not only asymptotic safety, but in general, other approaches to quantum gravity. Namely, the fact that if you just start from the Einstein-Hilbert truncation, so if your Lagrangian is 2 lambda minus r over 16 pi g. By power counting arguments, you would infer that this theory is non-renormalizable, at least, and I want to remark this, is perturbatively or power counting non-renormalizable. And the reason is that the mass dimension of the Newton coupling in 4 spacetime dimensions is -2. And Luca already suggests like one way to go forward in this would be to add higher derivative operators like r square, r minus square, and this fixes renormalizability, at least the strict or perturbative renormalizability that Luca was talking about, but spoils unitarity. So either one then has to modify something to get unitarity or conservation of probabilities back, or Ravan. It is mostly positive, but then you will see in actual normalization group computations, we will use Euclidean signature. So everything will look slightly different, and probably here I'm already using the signature that is convenient for me. But in any case, at this level, it doesn't change much. It's just an overall sign of the Lagrangian, so it doesn't really affect anything that I'm going to say. So yeah, we need to go beyond this picture. And at this point, we have several ways to proceed. And ways to proceed are, well, the framework of a quantum field theory works so well. Let's try to see if there is anything that we can modify or abandon or generalize in order to stay within quantum field theory. So stay within quantum field theory, and then one can do different things. The one thing that Luca mentioned was, well, re-understand the unitarity in a sense, or give up unitarity, or generalize the concept that we know. And this is the framework of quadratic gravity, interpreted as a fundamental theory, not just as a truncation approximation. Oh, quadratic, no. Then another option would be to abandon Lorentz invariance, maybe, if it works at all. And there are a bunch of approaches that use this. So for instance, Java gravity. One can also give up locality. And this results in a framework called non-local quantum gravity. And we will see a little bit of all of these things next in the coming weeks for during the workshops. And finally, last but not least, we can try to include non-perturbative effects, all-order effects, to see if we can fix renormalizability without giving up unitarity, Lorentz invariance, and all of that. And this is what we are going to see in today and tomorrow with asymptotic safety. And we are going to talk about non-perturbative renormalizability. as the key fix for why this does not work. And of course, if one realizes that nothing works in this case, so then we can also then understand or conclude that we have to go beyond the framework of quantum field theory. And here one can mention, of course, string theory that Ivano will tell us about today, or loop quantum gravity. And so on and so forth. And how does all of this connect with what Anna explained us? Well, at some point, once your framework for quantum gravity is understood, you know how to do computations and your theory is consistent, then ideally you would like to do calculations, compute scattering amplitudes, and one can just use the framework of scattering amplitudes, or connecting with what Anna explained you, one can write down an effective action, gamma effective, okay? So the Lagrangian then will be Einstein-Hilbert plus corrections. And these corrections, just let me use easy notation. So A r square plus B r mu nu square. Let me write this down, r mu nu, plus, well, this might be enough considering various identities that we have seen in the past days. And then there are terms at cubic order. So for instance, r mu nu square, and so on and so forth. And one can just, from the point of view of effective field theory, just one can just write down all of these terms and say, I parameterize my action in terms of these Wilson coefficients. And then the quantum gravity or UV viewpoint is that you need to compute this, at least some of these coefficients. The highest is the number of coefficients that you can compute, the more predictive your theory is. Ideally, of course, I mean, you would have a few parameters that are free that you have to fix by experiments, and the others you want to compute them. And instead, the EFT or infrared viewpoint is that you take this type of parameterizations for your action and you constrain the coefficients. And of course, the constraint, of course, come from essentially translating these actions into scattering amplitudes and then imposing positivity bounds, so unitarity, causality, analyticity, and all of these things. And then you will have constraints. And these two have to agree, of course. I mean, if your theory of quantum gravity predicts that A is 2 and EFT tells you that this coefficient is less than 1/2, then you have a problem. This is just the starting point for this lecture. So let's now try to go back into the some concepts that we have seen yesterday about renormalizability, and in particular perturbative renormalizability, and how to understand this in relation specifically with mass dimensions, scaling of couplings, and beta functions. And to this end, let me just consider a scalar field theory. So now we're going to talk about RG and perturbative beta functions. and the scaling dimensions. So let's take a Lagrangian, an easy one, just something like a scalar field theory. So we have just a kinetic term of this type, a mass term, not really super important for the argument. And then in general, we will have, we can write down a bunch of interaction terms. So we just have a theory. We know that I want to fix the field content to be scalar fields, fermions, whatever you have in mind. And then you have symmetries group. And then you can write down all of the possible interactions that are compatible with the symmetry of your theory. So in this case, it's just scalar theory. So you can write down essentially everything with this scalar field. So here we have 1 over n factorial, then an interaction coupling that I call lambda n, actually lambda tilde. These generally can have dimensions. So we are going to see this in a second. And then phi to the n. We work in d equal to 4. So Lagrangians have mass dimension 4. And this means, for instance, comparing to this term, this is mass square. This must also be mass square. So the field phi will have the dimension of a mass. So it's dimension 1. And from this, now you can analyze this term to understand what is the scaling dimension of these interaction couplings, the lambda tilde. So lambda tilde n times this that has the mass dimension m to the n, so it is plus n, must be equal to 4. And therefore, the mass dimension of this coupling that I'm going to call dn is equal to 4 minus n. And you know from, you may know at least from quantum field theory courses that this scaling dimension, the classical mass dimension of fields, tells us something about power counting renormalizability. In particular, if dn is bigger than 0, then the theory is perturbatively renormalizable. If dn is smaller than 0, non-renormalizable. And if dn is equal to 0, one has a marginally, a classically marginal coupling. And therefore, one to say something has to actually compute already some of the leading order terms in the beta functions. Now we need to relate these concepts to beta functions, and specifically why power counting indicates this type of behavior for the theory. So to this end, it is extremely useful to introduce a dimensionless version of couplings. So we say that lambda tilde n is the dimension of a mass to 4 minus n, so mass to the n, okay? So we can write this down. So in general, couplings will have, a dependence on the momentum scale. So this I can rewrite in terms of a coupling that is now dimensionless and a power of the momentum to the n, because this would match the mass dimension of this coupling. And now we can invert this relation. So just lambda n of k is lambda n tilde of k times k to minus the n. And we can try to understand now this in terms of beta functions. The beta function now for a coupling lambda n, let me call this beta n, is defined as k partial derivative with respect to k of the dimensionless coupling. Lambda n of k. And now we can just replace this scaling here to get, so first I apply it to this part. So here I would have like k2 minus the n, and then k dk lambda tilde n of k, plus if I apply the derivative to this object, I have 1 minus the n that goes down, and then k dk, but k times k2 minus the n plus 1, so once again k2 minus the n, times the dimensionless coupling lambda n of k. And then at this point, this should be the actually the lambda tilde n. And then this one again is the dimensionless coupling, lambda n of k. And this one, I can write this down in a different way, and in particular as lambda n of k times a function that is called the anomalous dimension, and it depends in general on the couplings lambda n. And this one, in order to match perturbative calculations, must be at least linear in lambda, because it would be the first correction to the leading order scaling, which is given by the canonical mass dimension. So how one writes down this equation is that the k, the variation with respect to the renormalization group time of lambda n of k can be written as this general form, which is eta of lambda n, which packs corrections to the leading order scaling that is given by the canonical mass dimension of coupling times lambda n of k. And this connects again to this argument. Why? Because this eta is a correction, is the leading order corrections to the canonical scaling. It is at least linear in the coupling. And this means that if one is in the perturbative regime, where your couplings lambda n are small, so they are just a small correction, the interactions are a small correction, add a small correction to the free theory. Then in a first approximation, I can neglect this term. And then if you solve that differential equation for the coupling, what you get is a scaling of this type. Something like that is proportional to k over a reference scale that is not really important, to minus the n, the canonical mass dimension. And the canonical mass dimension, now, if it is positive, it means that this quantity is decreasing, and therefore, as the momentum scale goes to high energies, this coupling is getting 0. So in other words, you are reaching asymptotic freedom. And at this point, let me also draw some plots that are important both to understand this very, very simple, to draw what we are seeing here with simple arguments, but also in general to understand the more complicated ones. And we need to understand this in terms of two different viewpoints, or at least it is useful to look at both of them. One is the renormalization group rounding of couplings. So you take into account the explicit dependence of coupling with respect to the renormalization group scale. So take this coupling here, lambda n, okay. And you have a dependence on the scale k. So for instance, in the case of quantum chromodynamics, you know that the theory alpha strong goes to 0 as k goes to infinity. That's the case of asymptotic freedom. And the coupling in that case goes to 0. So this is the case of asymptotic freedom. So the coupling alpha strong, for instance, reaches the value lambda n star equal to 0. But here, you should note that the coupling, here in principle, I'm drawing all possible values, but in perturbation theories, we are assuming, so we are doing everything by adding a small perturbation on the free theory. So actually, so the regime of validity is somewhere here. So we are covering this part of the diagram. That is where things are under control. Let's also look at this in another plot, via, in particular, parametric plot. This is important to understand what's going on in the so-called theory space. As the name says, this is the space of all possible theories, all possible quantum field theories, at least. And how does one parameterize these possibilities to just have in mind the space of all possible couplings, all possible interaction couplings for a given theory. And then each point in the theory space is one specific theory with one specific set of Wilson coefficients. So one would have here a coupling lambda 1 that depends on k, lambda 2 that depends on k, lambda 3, and actually many more that we cannot really draw on a whiteboard. But this is what we should have in mind. And each of the coupling depends on a renormalization group scale or a momentum, okay? And they all vary. And this means that as one considers the running of these couplings, one is also drawing a line or a set of trajectories in this space of theories. And these are the renormalization group trajectories. So in the case of asymptotic freedom, so when the couplings at very high energies go to 0, it means that they are reaching the free theory. So what they are reaching in terms of this space of theories is the origin. This origin is the free theory. And in terms of more technical terms, and we will see later why, this is also called the Gaussian fixed point. Or abbreviated is GFP. Okay. Why is it a fixed point. Well, in a fixed point means essentially that the values of your couplings are not varying anymore with respect to the time of your system. The time is the normalization group time. So if the initial conditions of our universe were such that we were sitting here at the Gaussian fixed point at the free theory, it would be essentially impossible to generate interactions if you are sitting here. If you are a little bit away from it, then you would be subject to a flow. So the normalization group transformations, if you are living here, then would drive you around this space of theories. But if you're sitting here, you're not going to move. It's a fixed point. And now, everything that is about perturbation theory, so one studies in quantum field theory, perturbation theories, what one does is to start from the free theory that we know how to resolve that exactly. And then we add interactions as small perturbations over the free theory. So what we are doing is to start from here and move a little bit away. So we are looking at, just to use the same colors, this part of the theory space. This is the part that we are looking at. And when we have trajectories that are asymptotically free, what we are doing is to move towards this Gaussian fixed point. This is what we are seeing with that type of scaling. If you have this type of scaling with the canonical mass dimension, which is positive, then we are going to get asymptotically free trajectories, okay? Vice versa, if we have an interaction coupling that has negative mass dimension, and this is, for instance, the case if n here is equal to 6, then the mass dimension of lambda 6 is -2. And you would infer from this that you are moving away from the Gaussian fixed point. And you would extrapolate, well, this is going to lead to divergences. Why? Because if you are moving away from this Gaussian fixed point, at high energies, you're not going to generate anything good. But at the same time, so if you extrapolate from that equation, okay, at least to leading order, you're also going at some point to exit the regime where your coupling is small. And therefore, the simple scaling dimension does not apply anymore. And what one actually needs to do is to compute corrections to that. And all of these may seem like a very trivial or maybe too naive arguments, but actually it is not, because what I'm writing down here is just the general form of beta functions. So you have leading order corrections, the leading order term, which is the scaling dimension, at least when you are close to the free theory. And eta, the anomalous dimension, which is a general function in principle of lambda. So all of the corrections are here. And you can imagine that these may not be simple in general if you think about the space of all possible theories. So this will have potentially a non-trivial dependence on lambda. But then you know that in perturbation theory, lambda must be small. So perhaps if you start doing loop computations in the perturbation theory and you compute the first orders of this, what you are computing is a Taylor expansion of the full function. So yes, you will get some corrections, but perhaps not the end of the story. And okay, so if you exit the perturbative regime, what can happen here? I mean, there aren't many possibilities here. So either the quantum corrections still keep this type of behavior and make it grow. It could bend like this, but then if we would bend and go back to the perturbative regime, when we would see that in perturbation theory, I would guess. And then there is one intermediate possibility, which is that this curve, due to effects that happen away from the free theory, bends the curve, but not too much. So this goes to something constant, but that is non-zero. Something that we can call lambda n star, which is constant but different from zero. And this is the intuitive, the intuitive generalization of the concept of asymptotic freedom to the concept of asymptotic safety. Nothing fancy, it means that as you go to very, very high energies, the theory becomes scale invariant, it reaches constant values of couplings, but these are not zero, so you are not reaching the free theory, you are reaching some theory with some fixed values of couplings, but since they are non-zero, the theory is interacting, okay? So here one is reaching the free theory. Here we are instead dealing with an interacting theory. And the concept of asymptotic freedom, so it comes from free, generalizes to asymptotic safety. And in terms of this diagram, what happens? Here one is reaching the Gaussian fixed point, so the origin of the theory space. And perhaps if values of couplings are reaching, in this case, something that is fixed but non-zero, then we are going somewhere here in the theory space. Somewhere, for instance, here. But something that you will see that in a bit is called non-Gaussian fixed point. And the fixed point and the fixed point we will see in a bit why. So we need to understand in general the corrections that are encoded in eta, because otherwise we are only going to study a very special part of the theory space. So all of our perturbative computations are valid if we are staying within perturbation theory. And of course, we already know, for instance, in quantum chromodynamics, that this doesn't happen at all scales. In quantum chromodynamics, in the infrared gets very, very wild, very non-perturbative. So we need, in general, to understand the whole space of theories and how renormalization group flows evolve. Okay, let me see if I have anything missing. This part, no. Yes. No, I mean, the fixed point could be very, very close to the perturbative one. So in principle, if it is close enough, so if the fixed point is non-perturbative but almost perturbative, you may even be able to see it within perturbation theories, and the people have also studied that in some ad hoc matter systems. Okay. But now, well, there is one more thing that I should mention, and it is that from the point of view of perturbation theory, or I mean, what is typically done in perturbative quantum field theory, one sees that this type of interactions with negative negative mass dimensions could lead to problems. And the typical strategy is to say, okay, this would lead to stuff that is uncontrolled. Then we select theories. It is the principle that Luca was talking about yesterday. We do select theories by imposing that they are strictly or perturbatively renormalizable. And this means essentially setting to zero the non-renormalizable couplings. So for instance, in the case of this scalar field theory, one would just eliminate anything that goes beyond, well, if we have like only positive powers, something like n bigger or equal than, so typically one would just keep everything that is satisfies this relation. Everything beyond is perturbatively non-renormalizable, and what one does is to set to zero the couplings that correspond to n beyond n equal to 4 in the perturbation theory. And this, as a student, may seem unintuitive or like quite not a random choice, but it's really a statement that one just throw out all of the interactions that are beyond those that are renormalizable. One would understand that they could lead to problems, but the power of what I'm going to tell you next is that there is a very nice way of understanding these setting couplings to zero in terms of UVT critical surfaces and the basin of attractions of fixed points in general. And all of this will at least sound, at least for me, it sounds much more natural than understanding it in general terms. Okay, so at this point, let's go to the next part. We are already at 45 minutes. I'm like halfway, right? Okay. So maybe if you like, you can have like a 1 minute or 2 minutes break. In the meantime, I just remove this and clean the whiteboard such that we can go at the on with non-perturbative beta functions and dynamical systems. Mhm. Because makes couplings safe, although they would look perturbatively non-renormalizable. I guess this is the interpretation, though. Do you know? I mean, for sure, I think that this would be my guess.
Yeah, safe.
Yeah.
Yeah.
Yes. While you would expect the perturbative, the divergence is like from a perturbative viewpoint. Okay. I think we can restart. In the meantime, I wrote down what we are going to do. So what we need is really a way to understand how to generalize, formalize these concepts of freedom and perturbative renormalizability to asymptotic safety, non-perturbative renormalizability, and ultraviolet completions in terms of certain points of the Fourier space. How do we say which points, which Bayer actions are going to be the starting point for to quantize the Fourier? And we also need to understand really what these relevant and irrelevant couplings mean. And we will see that in general, rather than talking about relevant or irrelevant couplings, we'll talk about relevant or irrelevant directions, because once we go away from the perturbative regime, it gets more complicated than talking about which coupling is okay and which coupling is not okay. And of course, in order to then see these things in practice and state whether a system displays asymptotic safety or not, one needs to compute the non-perturbative beta functions. But that's really hard computations, so we need to understand whether that is worth it in the first place, and why, and how exactly that relates to these concepts. And I think the best and the simplest way to understand the Wilsonian idea of renormalization in this, just based on the non-perturbative beta functions, is dynamical system theory, which is like a concept at the conceptual level. That's the easiest way of understanding these things. So we have, in general, these beta functions, these evolution equations for decouplings, k, dk. Once again, we have several couplings, okay? And then let's forget for a moment about eta d per se, which just write down a beta function that depends in general not only on decoupling n, depends on all of them. So lambda n and everything that you have in there. And if you see this as a dynamical system, this is just an autonomous, so independent of the renormalization group time, at least explicitly, ordinary differential equation for these couplings. The caveat is that perhaps one can have systems where one can compute the flow for functions. So for instance, if you consider going a little bit more to advanced topics in modified gravity, one would have functions of the Ricci scalar, okay? And then one can compute the flow really for the function. But all of these concepts essentially generalize, but it is much easier to just project whatever function you have in your action in terms of a set of couplings and compute beta functions. And then one would have a dynamical system, autonomous dynamical system in terms of a set of couplings. And if you see this as a dynamical system, what the beta functions tell you? So the beta functions in this case are just a vector field that tells you what is the speed of the flow. And from this point of view, it is very important to understand the speed of the flow, and in particular when the flow slows down and in particular stops. When does the flow stop? Exactly at fixed points of the beta functions, because if the beta functions is 0, it means that your coupling is not running anymore. So the fixed points are then defined, fixed points are defined by the following equation. So one would have lambda n of k star equal to beta n of all of these coupling. So star indicates a fixed points value equal to 0. And then this equation in general, if it is nonlinear, if it is a polynomial with higher powers, we'll have several solutions, not only the free theory, coming back to the case of quantum field theory. And in particular, from this, we can have two types of fixed points. The Gaussian fixed point, if the lambda n star is 0 for all values of n. And this corresponds once again to the free theory. And the non-Gaussian fixed point, if there exists at least one n, such that lambda n star is different than 0. And in this case, at least for one of the interaction couplings, the theory would be interacting. And of course, one can have mixed fixed points, so can be fully interacting or partially interacting. But typically, it is fully interacting. And the properties of fixed points, not only knowing if there are fixed points, but their attractivity properties are extremely important to understand the concept of relevant and irrelevant directions. So let's now understand, try to understand the...
Sorry, there's a question
Yes.
online. Does this nomenclature change if the non-vanishing coupling is a mass? Action would still be Gaussian.
Yes, I think so, because it would still be quadratic in the field, and this is what makes a fixed point Gaussian. Essentially, where the Gaussian comes from is from the path integral, because we will see in a bit the interpretation of fixed points is that of possible Bayer actions of your theory. And the Bayer action is the one sitting in the exponential in the path integral. So if you have a theory that is quadratic, that's essentially a Gaussian integral. So if you have fields that are quadratic, once you add the interactions, that breaks down. So you get something that is non-Gaussian. And it is important to understand what is the behavior now close to Gaussian fixed point, close to non-Gaussian fixed point. So in general, what is the behavior of the flow close to a fixed point? And it's easy to see. So we just start from our usual k decay lambda n of k. And this is in general equal to the beta functions. And now we linearize the beta functions around of a general fixed point, lambda star. So what that means, that would be beta of lambda n star, which is 0 by definition of fixed point, plus variation of the beta functions, so say this beta n with respect to lambda n, evaluated at, let me write maybe this, lambda m equal to lambda m star, so exactly at the fixed point. And here there is a summation over m of lambda m minus lambda m star. In principle, here there are, of course, other corrections. But if we are close to the fixed point, I can stop here and approximate this equation. And now this term gets as a very important role. Let's for now restrict to the case of one single coupling. Lambda. In this case, I would have that k decay lambda of k is approximately equal to derivative of the beta functions with respect to lambda evaluated at the fixed points times lambda minus lambda star. And then you can, this is of course, that depends on on k, okay? And then you can solve this linearized equation. And what you get is something like this. So the lambda of k will be approximately equal, close to the fixed point, at lambda star plus some integration constant. Let me write this in this way, minus theta. And here, theta is defined as the variation of beta, the beta functions with respect to lambda, evaluated minus, evaluated at the fixed point. And this is called the critical exponent. First, why critical? You can understand that well, it is clearly the important exponent that tells you like what's this linearized behavior around a fixed point. Why is it called critical? Because this comes from condensed matter physics, the physics of phase transition and the critical systems, where of course the physics is different, but structurally things are very, very similar. And so, for instance, one would see in condensed matter physics that one would have some correlation functions that scale with the temperature related to some critical temperature with some exponents. This comes from condensed matter physics, and structurally the equations are very similar to those of quantum field theory in the proximity of fixed points. So we know from, for instance, from condensed matter physics, one can show much more rigorously than in quantum field theory, probably that, and also have experimental verifications that this type of behavior happen. So for instance, in three-dimensional scalar field theory, we know that there is an infrared fixed point, the Wilson-Fisher fixed point, where this type of critical behavior happen. And structurally, things are similar as in the quantum field theory and perhaps gravity. So now this is the case of one critical exponent. You have this type of behavior, and this should remind you something that is that really looks like I removed that, but that looks like the scaling behavior close to the Gaussian fixed point. If not for the fact that here, in general, you have n non-zero value. I mean, this can be anything. And this critical exponent is the derivative of the beta function with respect to lambda at some fixed point value. So while in the case of close to the Gaussian fixed point, the linear order scaling is generally the mass dimension of minus the mass dimension of coupling, so it is an integer. In as one goes to other parts of the Fourier space, this can be in general a real number. Okay. And now we can understand here something about critical exponents, critical behavior. So we have like three cases. The case where the critical exponents, which now generalizes the canonical mass dimension, that is bigger than zero, which when it is positive, and this corresponds, remember, case of one single coupling to a relevant coupling. Why relevant? Because as I increase the energy scale, and if theta is positive, this guy is shrinking, he's getting smaller. And this means that the flow is getting closer to lambda star. So something like this is happening. So here we have our fixed point value, our lambda n star, And then there can be RG trajectories. Depending on the integration constant C, we can have something like this, or something like this. Everything approaching this fixed point, depending also on the initial conditions. We have the case of theta equal to 0, which is marginal coupling. But in the case of marginal coupling, it's a little more complicated because in principle, this would be constant, but then there can be next to leading order corrections that decide what the flow does. And then the case theta smaller than 0. That is the case of irrelevant coupling, and that's the opposite behavior. So it means that the lambda goes away from lambda star. And now this already with this single coupling tells you a little bit how things generalize away from the Gaussian fixed point. So you have here like one single direction because there is one coupling. So it is essentially the real axis where you have this lambda k. This is lambda star. What this equation tells you is that if you are close to here, and for instance, theta is positive, if your initial condition is here, your flow is approaching the lambda star from this direction. If you're here, you're going in this direction. And similar for irrelevant, you would move away from both directions. And now this is important to understand, to generalize this argument to the case where in general we have multiple couplings. So let's go to the case of multiple couplings. Oh, oops, okay, I forgot. That's great. So we now go to the case where we have multiple couplings. In which case, that type of relation generalizes just to a vector of couplings. So your lambda n will essentially, sorry, your k decay of lambda n k by linearizing the flow around the a general fixed point. So the first term once again will be 0, and then we have the second term, which is the variation of the beta functions, and we can essentially write this down as the variation of the beta function with respect to the couplings evaluated at the fixed point times lambda minus lambda n. Sorry, must be actually something like this. And then lambda minus lambda n. And again, close to the fixed point, what we had before, that was just the simple variation of beta with respect to the coupling, turns into a matrix, which is called the stability matrix. And is the variation of all beta functions with respect to the couplings. And this stability matrix is extremely important. It brings the properties of each fixed point of your system once you evaluate this at a given fixed point. Because then this will have, in particular, some eigenvectors, okay, and some eigenvalues, which will be exactly minus theta I, so related to the critical exponents of the systems. This will be eigen directions, and this will be critical minus the critical exponents. So this is related to the critical exponents. Okay, and this will then look like this. So it will be a sum of some coefficients, then our eigen vectors, and k over k naught over minus Tm, and the Cm depend on the specific coupling. Yes, exactly. So these are the eigenvectors of the stability matrix, and these are the eigenvalues. And why all of this is important? Well, because the eigenvectors tells you about the attractivity properties of the fixed point. And at this point, so we may have like multiple fixed points, okay? And multiple directions. And in particular, these AI, the eigenvectors, do not need to align, do not need to be parallel to the couplings, to the axis of the Fourier space. So for instance, if one has a Fourier space of this type, so with couplings lambda 1, lambda 2, lambda 3, and we have a fixed point here, the eigendirections could well be like something like this, okay? And then one would have different attractivity properties. So for instance, on one direction, the flow is attracted towards the fixed point. So generalizing what we have seen here. So on the one direction, it is attractive. On the other direction, it is repulsive. Okay? And then the trajectories here will be of this type. Okay? And exactly because there could be critical exponents that are positive, negative, marginal, and so on, we would have different types of fixed points. And in particular, so if theta I is bigger than 0 for all I, then the fixed point is fully UV attractive. If it is negative for all I, then the fixed point is fully IR attractive. That means all trajectories will reach the fixed point as k goes to 0. While in this case, all trajectories would reach the fixed point as k goes to infinity. And now there is the most general case that is a fixed point that has some positive critical exponents and some negative critical exponents. And this would be the case of a saddle point. And this is the case in general. Typically, there is a mixture of positive and negative critical exponents. Now, why this is important? It is kind of important because from the if one has the full non-perturbative beta functions, one can compute the fixed points and the attractivity properties, so the critical exponents. And from there, one already has an idea, and actually also based on the divergences of the beta functions, if there is any singularity. One already gets an idea about the phase diagram, about the global properties of the renormalization group flow. And just to give you an extremely simple example, in mathematical analysis 1, okay, when you have to compute when you want to draw a function, okay, what you do is to compute, to understand the special points of a function. So you compute the derivatives and see where they vanish, where they diverge, and the sign of the derivatives, and all of that. And then once you have identified, yes. Okay. Oh, okay. You're answering, okay. So if, yeah, essentially from the special behavior of the function in some points from asymptotes and vanishing of the derivatives and minima, maximum, you can understand how the function looks like. And here is a little bit like the same. If you understand, if you know the beta functions, you compute the zeros, so you know the fixed points. For each fixed point, you compute eigenvalues and eigendirections, so you understand how if the flow, the linearized flow behaves like close to here, then you can infer how the flow looks like. And just to give you an example, so let's just take the case of a theory with two couplings. Okay, and then we have one fixed point here. The Gaussian is essentially always there. And typically, what happens with the Gaussian fixed point is that the eigen directions are aligned with the axis. So one would have, for instance, one attractive direction here and one repulsive direction, okay? And this is the case if one has one coupling, for instance, with negative mass dimension and one coupling with positive mass dimension. And perhaps we have another fixed point here that is fully attractive. And once we know about these two things, we know that there will be trajectories here that are attracted towards the Gaussian fixed point, but then they meet the repulsive direction of the other coupling with negative mass dimension, and then they are repulsed in this direction, and we know that these trajectories will look like this. But then once one gets closer to the non-Gaussian fixed point with this type of structure, so all of these attractive directions, all of these trajectories will end up here. So you see, once we have access to non-perturbative functions, fixed points, and critical exponents, we understand a little bit more about the global structure of the renormalization group flow. And in particular, there is, well, one property about flows with multiple critical exponents or with multiple fixed points is that there will be trajectories connecting the different fixed points. So for instance, in this case, there will be one trajectory that connects the two in this way. Not really like that, but yeah. And this is called separatrix. Yes. And now, at this point, there is one more concept that is important, that is the basin of attraction of a fixed point. The basin of attraction of a fixed point is defined as the set of points or initial conditions in the Fourier space, such that if you solve the flow for that initial conditions, then you arrive at one particular fixed point. So of course, the basin of attraction depends on the specific fixed point, because if I, for instance, for this case, if I initialize my flow here, I will end up at this fixed point because I immediately meet these two attractive directions. But if I initialize my flow here, now, on the attractive direction of the Gaussian fixed point, I'm probably going to end up here. So in this case, for instance, the basin of attraction is just one line, and the rest will be in this part of the Fourier space will end up here. this is just based, of course, one needs to solve the flow then to understand if non-trivial things can happen, but more or less you can infer what happens once you know about the critical, about fixed points and critical exponents. And why the basin of attraction now is important? The basin of attraction is extremely important to understand how many free parameters your theory has. And this is related to the number of relevant directions that you have. And you can see this from here. So say that in this theory you have 10 couplings, okay? And then 3 of them come with positive critical exponents. And the others instead have negative critical exponents. When you have a negative critical exponent, this contribution to the linearized beta functions will tend to grow unless the initial condition, Cm, your integration constant, is 0. Instead, if you have a positive contribution with a positive critical exponents, the contribution will get smaller. So if I now, these are just general initial conditions that select the particular renormalization group trajectory. What do I have to do in order to sit on a point that leads me to this fixed point, to the, I did not write that now, but okay. So if I want to reach the fixed point, then I need all the contributions to get smaller, okay? And therefore I need to set to 0 all the integration constants associated with irrelevant directions, okay? So I have to set to 0 as in my initial conditions, all of the constants, the integration constants that are associated with negative m. And this essentially turns into constraints for the flow. And the remaining Cm select the renormalization group trajectory on the hypersurface where I reach the fixed point. And this means that in this type of theory, so the number of initial conditions practically will be reduced by my by the requirement that I reach a given fixed point, okay? And therefore I will be left in practice with a fewer number of experiments that I have to make in order to select the specific trajectory among those that reach a specific fixed point. How does this work, for instance, in perturbation theory? So let's say that I have a system now with 3 couplings once again, so lambda 1, lambda 2, and lambda 3. And they focus on the Gaussian fixed point, so standard perturbation theory, and I'm here. Okay. Let me just change this, just because couplings with higher dimensional operators tend to be more irrelevant. Okay. In this case, say that here I have 2 couplings, these 2 couplings, lambda 1 and lambda 2, that have positive mass dimension. So they are associated with attractive directions. Okay, and then there is this one that instead is associated with repulsive direction. The statement then that one makes in the context of perturbation theory is this is an irrelevant direction, and therefore I set it to 0. So one practically considers only the Lagrangian in this sub-theory space. So one is literally projecting the theory in a space such that the renormalization group trajectories are under control. So if I initialize my flow here, I would, for instance, flow to the to a theory that is UV complete because it reaches the Gaussian fixed point. Okay. So the statement of perturbation theory is that one limits oneself to couplings that are exactly relevant, such that one has flows that are controlled close to the Gaussian fixed point. But this picture now can be generalized in the case of non-Gaussian fixed points, because if there is a Gaussian fixed point here, so things are less clear than in perturbation theory, because in general, the eigendirections do not align with the axis. So one, once again, can have something like really linearizing close to the flow. One can have something like this, for instance, if say that we have something that is a saddle point, okay, something like this. But then in general, if one goes away from the non-Gaussian fixed point, the set of initial conditions such that I reach the fixed point, it gets a little bit more, it is not flat, the UV critical manifold. So you can have something like, I'm not really good at drawing, but something like this, curved, such that for all points here, let me actually restrict to the case where this part is attractive, okay? And then there is one direction that is repulsive that exists out of the whiteboard. Then if you're sitting here on this UV critical manifold, which is the generalization of just restricting to relevant couplings in the case of perturbative quantum gravity. Then for all points in the critical manifolds, I reach the fixed point, okay? And if instead I depart my flow just a little bit outside of the critical manifold, then my trajectories will go away, okay? And now, why all of this is important in the context of quantum field theory? It is important because our beta functions typically look like this. So there is the anomalous dimension that depends on all of our couplings. So not only lambda n, but all of them. We have the scaling dictated by the mass dimension, and then we have our coupling n, lambda n. So when I solve this fixed point equation for the beta functions, there will always be the Gaussian fixed point. So perturbation theory works. I mean, we have the Gaussian fixed point as one possibility for the Bayer action in our system. But in general, if as soon as there is an eta, so an eta that is nonlinear in the couplings, minus something that is constant, in general, this part can have zeros. And if it has zeros, what does it mean? That the theory can have multiple ultraviolet completion. The Gaussian fixed point is not the only one that I can reach asymptotically. It means that asymptotically I may have a Gaussian fixed point, and in principle, several non-Gaussian fixed points. Okay? And these are those that have at least one direction in the UV that is ultraviolet attractive. Okay? And what does it mean that I can reach them in the ultraviolet? And if I can reach them in the ultraviolet, they are possible ultraviolet completion for the theory. So all of this, and this is really powerful, tells you that the beta functions, if you can get them exactly, non-perturbatively, tell you, without you saying anything about the theory, they tell you what are the possible Bayer actions of your theory. You have to, of course, specify what is your field content, your symmetry. And once you have done that, your beta functions tells you, well, your possible ultraviolet completions are this, this, and this. These are the UV completions. And I will take 2 more minutes, okay? What do I do with this ultraviolet completion? Then I can try to define the theory with respect to different ultraviolet completions. So with respect to the Gaussian fixed point, but perhaps it doesn't work because the theory is not asymptotically free, or with respect to other fixed points that I may find by solving these fixed point equations. The fixed points will come with a number of relevant directions. The number of relevant directions then equates the number of free parameters in your theory, because remember that you have to set some constants, some integration constant to 0 if you want to sit on the UV critical manifold. And with this, you can compute your effective action based on a finite number of parameters, which now generalize the concept of relevant directions of quantum field theory. And this is precisely the concept of the generalized idea of renormalizability or asymptotic safety. And now let me overuse the term of asymptotic safety by including asymptotic freedom. The requirement is that there exists a fixed point that can act as ultraviolet completion for the renormalization group flow of your theory that comes with a finite number of relevant directions. And this finite number essentially coincides with the number of free parameters that you would have in your theory. So this is a measure of the predictive power. That's why one wants this to be as small as possible. And the theory will tell you about this. And now, why this is important in gravity to conclude this hour and a half. Let's go to the case of gravity. The case of gravity the Einstein-Hilbert action has two couplings that are the cosmological constant and the Newton coupling. And now let me represent here the cosmological constant, or the dimensionless version of it, by lambda. The dimensionless version of the Newton coupling by G. And now lambda, has a positive mass dimension, has a mass dimension +2. It goes as m squared. And therefore it is an attractive direction with respect to the Gaussian fixed point. G has a negative mass dimension, -2. So it is repulsive. And this is the reason why gravity in the Einstein-Hilbert truncation cannot be asymptotically free. So if you depart your flow here, you are going to follow this type of trajectories, for instance. And perhaps one would infer that you have perturbative non-renormalizability by extrapolating beyond the perturbative regime. But what could happen, and that what has been proposed by Weinberg in 1976, is that actually once you leave the perturbative regime, there can be another possible ultraviolet completion for your theory, such that actually you are not going to diverge, but your flow is well defined with respect to the non-Gaussian fixed point. How do we test this? We need non-perturbative beta functions, and this is what we're going to discuss in the next hour with Benjamin. So thank you.